Welcome to the webinar, Modern Fixed Restorative Materials, Selection, Preparation, and Clinical Success. This lecture is being presented by Tremaine Watkins, CDT, and we will begin shortly. And now it is my distinct honor to introduce Tremaine Watkins, CDT, Director of Strategic Education. Tremaine has been working in the dental industry for more than 35 years. He has extensive experience fabricating analog and digital prosthetics with expertise in implant-supported and retained restorations. A respected lecturer on both laboratory and clinical aspects of restorative dentistry, Tremaine trains technicians and provides clinical support in case planning, troubleshooting, and implant placement. And with that, I get to say, take it away, Tremaine.
Thank you very much, Jessica. And don't let Jessica fool you. Like, none of this would happen if it weren't for her and all the hard work she does behind the scenes. I'm the pretty face, but Jessica makes it all happen. So thank you very much, Jessica. The great program that you guys get to enjoy, NDX education as a whole, is because of all of Jessica's hard work. So let's talk about fixed restorative materials. A lot of times I'll do presentations about stuff that we only use every once in a while. Maybe you do an all-on-X case once every month or two in your practice, or even with removables. But today we're going to be talking about the stuff that's kind of the bread and butter of what you do every day, day in and day out. And so I really hope that when we're done with this, there'll be some pearls that you can use tomorrow in your practice. So here we go. Couple of business slides as well. I am a full-time employee of National Dentex Corporation, and I was paid to make up this presentation. But there was no commercial support for this other than that. So any products that I talk about or whatever, because I found them helpful, nothing beyond that. So for our learning objectives tonight, we want to, have a little bit deeper understanding of patient evaluation and material properties, so that when you're dealing with a specific case, you know what's going to be the best option. Indications and contraindications, talking a little bit about case design and how to use our planning process to get the best restorative result. And then we're going to do a little overview of the laboratory digital workflow as well. These are some resources that I found helpful for additional reading on this topic. So let's talk about shade. Anytime I'm trying to make up a presentation, I kind of have to figure out, where are we going to start? And there are a lot of, as you guys know, there are a lot of clinical aspects to what we might consider a successful case or a failed case. But if we ask our patients, that few problems are going to be more noxious to them than, especially a small case where the shades don't match. So one of the things we got to think about is, what does a successful shade match look like? So if we're doing a full arch case, it's basically hold up the shade tab and let them pick one. Sometimes, again, there needs to be some steering, because you might tell a person, paper white might not look awesome with your face, and helping people understand that. But the cases become a little more challenging when we're doing, one case I remember in particular, we were replacing, I want to say, number 8. And so the interesting thing about this person's shade was that 9 was the darkest tooth in their aesthetic zone. So if I would have matched that tooth, those two teeth would have looked perfect. But then from a smile perspective, I kind of would have made their whole smile look darker. So it was an interesting case, because we wound up going a little bit lighter. And I feel like I had a good conversation with the patient, because the patient was very happy with the result. But we kind of brightened up the whole smile with an eye towards, at some point, restoring number 9. But even with the current configuration we had, the person said, yes, my smile looks brighter and prettier with this lighter shade. One other thing we need to think about is that monolithic restorations especially create color different than a tooth. As you guys know, with a natural tooth, the light passes through the translucent enamel, is altered by it, bounces off the more chromatic dentin, and then reflects back to us through the enamel again. So there's a certain depth in a natural tooth that is difficult to replicate with a restoration where most of the light is bouncing off the surface. So we need to figure out a way to create that illusion of depth. So we'll talk about taking photos, but as you're working on these cases, you need to kind of look at the nature of the shade and make sure that you communicate it accurately to us so that we can replicate it. Now, I love this photo for translucence, and it's probably not for the reason that you think. So this photo originally came from a presentation back when all ceramics were new, and they're like, oh, all ceramics are awesome and PFMs are bad. But that's not why I put this in here. I put this in here because more translucence is not always better. You know, sometimes we're trying to cover up a dark underlying dentition or metal post or a metal abutment, and we need a restoration that has some more opacity just to block that out. Sometimes we're dealing with a situation where if we put too much translucency in a restoration, let's say the person's teeth are a 1M1, we wind up with a crown that looks like a D2 because that extra translucency also decreases the value. Third thing to keep in mind is that in general, more translucent materials tend to be a little bit weaker. So we might not be able to use something that has the degree of translucence we'd like ideally because of the strength requirements of the case. So when you look at this slide, I don't want you to think, oh, I want HT ingots all the time. I want you to think, hey, one of the things I got to think about when I'm looking at a case and at a shade is what is the ideal translucence for this patient? And it may not be the maximum amount. As an aside, there's a lot of things that you can do clinically to control dark underlying shades. Perhaps you do root bleaching, perhaps you do composite basing out. One of the things that you'll realize pretty quickly as you're doing more comprehensive cases is that if there's one dark shade, controlling that can dictate the materials for a 6 or an 8 unit case. So maybe if you control it clinically, it gives you better restorative options. So anyhow, translucence is a lever that we can pull, but maximum translucence on every case is not always the best solution. So when I started in this field, the ends of this spectrum were very far apart. We had on the beautiful end, that's what this picture is meant to represent, we had hand-layered feldspathic veneers, which were so fragile that we had a hard time finishing them in the laboratory without breaking them. And then at this end, we had gold crowns that are pretty much bulletproof, but maybe somewhat lacking in cosmetics, depending on what you think about cosmetics. What's cool is that in one of the many, many improvements that we deal with today is that our strong material that we use most of the time, zirconia, has some very nice aesthetic properties, and some of the super fragile, we don't need to use such super fragile materials to get really great aesthetics. So the two ends of the spectrum have pulled together quite a bit, which is nice for us. But there still are variations in material based on strength and aesthetics. So part of your evaluation of your patients is how much strength do they need and what do they prioritize? In other words, you may have patients that are going to want the maximum aesthetics, and we might wind up using a less strong material, even though they have a history of parafunction. And so you're going to need to talk to them about, we're going to be making a night guard for you. It's going to cost this much, and you're going to have to wear it every day. If you don't wear it and the restoration breaks, I'll be happy to replace it for you. There'll be a fee for that. And on the other hand, you may have patients who could benefit from a more aesthetic material, but they say, I want something that's bulletproof. I don't want any problems with this, and I'm willing to compromise a little bit on the aesthetics. I mean, ideally, we want to get the perfect aesthetics and the perfect material, but part of your patient conversation is deciding what they prioritize and making sure that we make their priorities ours. Strength. We've all been living in the zirconia world so long that when zirconia came out, for some reason, everybody in our industry decided that flexural strength, which is this, basically, the amount of force that it takes to break a precisely manufactured bar of the material that we're testing in the middle, is what strength means in dentistry. And in the ceramic world, that's fine. Now, one of the things we have to keep in mind about ceramics, and for those of you that have used metal restorations, you know that metal has a certain amount of toughness. So its absolute flexural strength is actually lower than some of the zirconia materials we use. But what's interesting is that when you apply a lot of force to it, it doesn't either hold or fracture like ceramics do. It tends to deform a little bit, which can be nice. So a lot of times with ceramic materials, we need super high flexural numbers because they have no give in them. But now that we're starting to get into the era of 3D printed digital materials, I think we need to kind of take a step back and say, hey, there's more to dental materials than flexural strength. After all, we can place a 1200 megapascal flexural strength zirconia crown, but natural teeth, as you guys know, are in the neighborhood of 400 to 450. But we need to start looking at other things. We need to look at such things as hardness, ductility, modulus of elasticity is going to be pretty important, water absorption or the lack thereof, and other factors. So when you start seeing some of these new permanent printed materials come out, they're not going to be 1,000 megapascals. I mean, I've seen some that are, up in the 200-300s. And so you got to ask yourself, well, what does strong enough mean in this world? And I think what we're going to have to do is we're going to have to look at all the properties of a natural tooth and decide, where that falls. Because after all, there's a lot of people who, back when Empress was out, who would restore Milla Empress on their CEREC and restore molar with it. So even that's a material that had maybe 120, 140 megapascals of flexural strength. So I guess what I'm saying is that let's all brush up on on what strength and durability of dental materials really means, so that way we can kind of separate the hype from reality for new materials and be open and take advantage of the new materials that are coming out, while at the same time not placing stuff that may look good on a marketing slick, but really isn't going to have the durability that we want to deliver for our patients. The cool thing about the restorative materials we're going to be talking about tonight, because I'm going to kind of steer clear of printed permanent materials at this time, are going to be materials that have been in use for 20 years or more. As CRA says, the ultimate test of anything is clinical success. So these are all materials that have shown clinical success. Just putting that out there. Adjacent materials. This is really, really important. A lot of times, as we're working with a multi-unit case, sometimes each tooth might have indications that would steer us one way or the other. So for instance, if you look at this person's beautiful teeth, these teeth have a lot of translucency. But if this tooth had a really dark stump, I might wind up wanting to restore this with something that has a little more opacity to it, and this was something that has a little more translucence. So I could prescribe two different materials, or you could prescribe two different materials, and we do our darndest to make it. What we found clinically is that if you take two dissimilar materials in the aesthetic zone even if they look pretty good on the bench, because of their varying optical properties, you'll see a difference in the mouth. So, like we talked about, the first thing is if there's something that requires that you use a less translucent or a stronger material than you'd otherwise like, think about what clinical steps can I use to negate that problem so I can use the materials I want. Can I bleach this dark root and get a good result, for example? Or can I anodize this implant abutment? Or should I use a zirconia abutment in the middle of this case in order to use the, let's say, Emax materials that I'd really like to use? So that's a big part of treatment planning. But I'll talk about kind of a couple tricks you can use when you need to use dissimilar materials, but I think that we're getting to the point with zirconia veneers and with different things we can do with implant abutments and stuff to where we have more possibilities of using more than one material on a case with varying underlying shades and stuff like that to get a really good result. One other thing I wanted to touch on here is that, as you guys know, if you've done very much with aesthetic cases, we can kind of talk about getting the teeth in the right position. The easiest way to get an awesome looking restoration is to restore a tooth that's in the right position and that has the correct gingival position. So sometimes you may need to do a little bit of crown lengthening or orthodontics as well to be able to get that really awesome result that your patient wants. So I guess this slide's about preparing the substrate to get an awesome result. Monolithic versus layered. When I grew up there, like I said, gold crowns were the only monolithic we were doing. These days, most every restoration we're delivering is monolithic. So what's the difference? A monolithic is basically the whole restoration is one material. So if it's a monolithic zirconia, it's all zirconia. If it's a monolithic lithium disilicate, the whole thing is lithium disilicate. With layered, this is a PFM, obviously. Since the metal under PFM isn't that pretty, usually the whole thing is layered with ceramic, or you might use a metal lingual. But so we have dissimilar materials and an interface layer. And what this is showing is that there is a potential for delamination, but we'll talk about that a little bit more on the next slide, because I think that can be a bit more of a straw man than otherwise. This slide shows delamination from Dr. Christensen, and you can see within the slide why it delaminated. Dental porcelain needs to be well matched to the underlying substrate so that as it's fired and then cools, the ceramic has a slight compressive force on the understructure. That gives you the strongest possible restoration. But this material is fairly weak, and this material is quite strong. So normally what we need is we need a coping that's like the external surface of the crown, but smaller, like I'm kind of drawing on here. In this case, we didn't have proper porcelain support, so needless to say, it led to a fracture. Another thing that we saw way back when layered zirconia first came out, which is now a long time ago, is that a lot of laboratories had only layered porcelain on various kinds of metals, and they didn't realize how different the coefficient of thermal expansion of zirconia was. So some people would foolishly use metal ceramic porcelains on zirconia and then wonder why it broke all the time. So what we found today is that zirconia is actually a better substrate for layered ceramics than metal, because each metal alloy has a slightly different coefficient of thermal expansion. So when porcelains are being developed, they have to work with a pretty broad range of CTEs. With zirconia, the coefficient of thermal expansion is a single number, so the porcelain can be really dialed in and get a nice result. So even though we saw a little bit of this back in the beginning, I think now more than ever, if you want to use a layering ceramic or you need to use a layering ceramic, we can get a good result and you're not going to see this. We'll talk about a couple other little tricks with that. The one nice thing about monolithic restorations is that it allows you to do very exact digital copies. So for instance, I've been reading a little bit from Dr. Dawson about with his procedures for prototyping and the like. One of the cool things about using monolithics is that once you guys get the provisionals all dialed in, then we can exactly copy it. We'll have a scan of that design in 3 dimensions, and then we'll be able to exactly replicate that so that the arc of lip closure and different things like that are perfectly replicated. We don't have to use matrices. So I think that the ability to exactly replicate a well-developed prototype is one of the huge advantages that we see with monolithics. Because a lot of times we're only looking at them because they're a little bit less costly and they sometimes use a little bit stronger materials. But I do think that that precise replication of well-developed provisionals is an advantage for them. So what are kind of our modern restorative materials options? We're going to kind of flip through these. We got monolithic zirconia, layered zirconia. I'm going to group lithium silicate and disilicate because of patent issues. These two have developed, but functionally, their physical properties are so similar that they can be treated as the same thing. PFMs and full cast. I feel like this is kind of the, like I said, the waterfront of proven materials, leaving out 3D printed for tonight. Zirconia, what is it? We'll start with it because obviously the majority of the restorations that are being delivered in the fixed world today are zirconia, and advances in the materials seem to be making it more popular than ever. So the way that we use it in the laboratory is dental manufacturers take zirconia oxide that are mixed in very precise proportions with other materials, and we'll talk about that in just a minute, into 98 millimeter discs, which we call pucks. They compress it and smush it so that it's like a super compacted snowball, basically. And then we mill the restorations from that, a little bit oversized, actually, and then they're centered in a at a very high temperature to achieve the final strength, color, and shape. So, like we talked about, zirconia is a ceramic. It's the white crystalline oxide of zirconia ZR metal. The main, you can't call it alloys in ceramic, but if it were metal, it would be an alloy. The other element that's added to zirconia is yttria, which affects the development of the crystal lattice in the zirconia, and it makes the material extremely hard and strong. The amount of yttria, which is sometimes referred to as the mole of the zirconia, has a huge effect on both the physical properties and the aesthetic outcome for the product. I don't know if you guys remember when zirconia first came out, but when 3-mole zirconia first came out, it was an extremely hard, extremely white material that we had to stain the snot out of it to try to get any kind of decent result. It was almost like a white gold crown. Many times to get a decent aesthetic result, we wound up layering the whole thing just to kind of try and hide that zirconia understructure. Now, here's one of the interesting things about 3-mole zirconia is that, as you know, every material has microscopic flaws in it. And when we apply stress, the focus of the stress becomes the point of those microscopic flaws. Well, if you get down to the very point of it, you're going to have 2 crystals or just a few crystals of zirconia around it. So here's the interesting thing about 3-mole zirconia. So when you apply that force at the point of the crack, the little crystals right adjacent to it absorb that force, and they do a thing called phase shifting. So they shift from tetragonal to monoclinic. And you're like, why do I care about this? The reason you care is because a monoclinic crystal is slightly bigger than a tetragonal crystal. So if you will, you put force on those crystals trying to separate them, and what actually happens is they grow a little bit and they sort of push back on the force that's being applied. This is why zirconia is so strong, this transformation toughening. Now, when we add more yttria, it can create somewhat more translucent or even much more translucent zirconia. But what we found, especially when the early 5-mole zirconias came out, I remember this, that transformation toughening effect seemed to be less pronounced. And so we lost a lot of that super awesome strength that was what made zirconia so fun. So what we're seeing today is that, well, there are single shade pucks or single translucent or single Y pucks, you might say, that are still being used. What's more common these days are multi-layers, and they're either multi-layers of shade, in other words, where this has a little bit of blue added to it, and then this has more chroma, so that as you mill it, it has kind of a gradual translucence, or these, which are getting more popular, where we have not only different shades in the puck, but we have different amounts of yttria. So here in the what's going to be the gingival portion of it, we have the 3Y that's stronger and a little more opacious with a little bit of chroma added to it. And then we might go all the way up to a 5Y where we have not only the appearance of translucence from blue modifiers, but actual translucence. So these kind of materials give us the ability to mill a monolithic zirconia that has a beautiful aesthetic result. So that's part of why, besides cost, one of the reasons why layering isn't as popular anymore is because we can use these polychromatic and multi-Y, I guess you could say, composition pucks to get a very, very nice restoration. So having talked about the nature of zirconia, I guess, let's talk a little bit about monolithic zirconia. Obviously, these are the most popular restoration these days. And even weak, quote unquote, anterior zirconia, often at 700 and 900 megapascals of flexural strength, is much stronger than our 400 to 450 megapascal natural dentition. Again, as we talked about, because it's brittle, we need a little bit of extra strength in there, but you have in your laboratory have more options than ever in selecting zirconia. So one of the things you want to do is kind of talk with your laboratory about, hey, what's been going on with zirconia lately? What zirconias are you having success with? And take advantage of these wonderful new materials that are available. So you're like, if there's all these awesome materials, why are we even talking about layered zirconia? Well, one of the things that you'll find is that there may be situations where you want to do a lithium silicate, lithium disilicate restoration and a zirconia next to it. Let's say you're doing a veneer and you've had better success with bonding Emax and you want to do a bridge next to it. Well, to get the best match, not only in terms of shade, but in terms of optical properties, you might choose to do a bridge with labial layering or micro layering on the zirconia, and then the lithium silicate veneer next to it, so you don't get as much of that change from the one to the next. We'll talk a little bit about zirconia veneers and the options that are there. One thing that's nice about layered zirconia is that the same zirconia that can be made monolithic can also be made layered. So let's say you had a case that had 11, 12, and 13 on it. And you're like, well, I want to do monolithics for 12 and 13, and I'd like some layering on 11 to nicely match the translucence of 10. No problem. We can design the zirconia so that the biting surface of 11 and all of 12 and 13 are to full contour, and then cut back 11 for layering or micro layering on the facial. So one of the cool things about zirconia is because we don't have to opaque it, especially with modern pretty zirconia, we can put the finish line wherever we want to. We could do the whole lingual out of monolithic and then layer the labial. So again, are you going to be doing hundreds of layered zirconia restorations in your practice? Perhaps not, but you can, in those situations where you need that little bit of extra aesthetic oomph, you can be confident that delamination really isn't a thing anymore with laboratories that are doing this process consistently. And it gives you another lever that you can pull when you need to match a veneer, say with a bridge, or a veneer with a implant crown, something like that. So using zirconia. Now, I bet you guys all have materials that you use in your practice that works awesome for you. And when you talk to one of your colleagues, they're like, I hate that stuff. Doesn't work worth a darn. We talk a lot about dentistry, like what works in your hands. Laboratories aren't different. We each kind of work with the materials that are out there and find things that get a better result for us. A lot of times your laboratories will have multiple options for zirconia. What I would recommend is you're kind of fine-tuning your restorative selections for your aesthetic cases is try the different options that your laboratory offers on lower stakes aesthetic cases. Like you might try using an aesthetic zirconia on a premolar just to see what it looks like. Send in photos and really work in the details and then see what it looks like. It would be good for you to have a gut feel of when I prescribe this zirconia, I'm going to get this result before you're actually doing high stakes aesthetic cases. And let's say you've worked through this process and you're like, I'm really not getting the results that I want. Give your laboratory a call and talk through, take some photos and share those with the results that you're getting. Your laboratory can kind of your lab has more time to keep up with materials trends than you might, so they can kind of talk about like, wow, okay, I see that. Let's do whatever to kind of work through this result to get you the aesthetic results that you need. Lithium silicate or disilicate. These are an awesome aesthetic restoration. Until not too long ago, because of the ceramic content in them, they were really the only option for partial coverage bonded restorations. Of course, these can be used as monolithics. They can also be micro-layered for enhanced aesthetics. One of the nice things about these materials is that you don't only have a variety of shades that you can choose from, you also have a variety of translucencies. So within the monolithic world, you have nearly 50 different puck or ingot options to choose. So it gives you a lot of different options. Now, these days with MDP-based primers, you can do zirconia veneers. So today, if you're doing a zirconia bridge, you could bond a zirconia veneer very predictably next to that. But there are going to be times when you're doing a thin restoration, and the intrinsic translucency of these restorations will look a little bit nicer than potentially than a zirconia might. On the other hand, sometimes if the biomechanical load isn't too severe, you can do a 3-unit bridge, first premolar to first premolar with these materials. These usually aren't the best option for clinical shade control. There are some high opacity ingots, but they usually require a fair amount of layering to get a really nice result. So whereas with the zirconia, if you're using 3Y, you can go down to as little as 0.8 of a millimeter of occlusal and axial reduction. With these, you're really going to get a better result with 1.5 millimeters for full coverage and 0.6 to 0.8 millimeters for veneers. One other thing I would say with this is it's been a while since I saw this study, but there was a study that came out that compared basically a thick cemented lithium, we'll just say lithium disilicate restoration with a thinner, so 1.5 cemented against a 1 millimeter bonded. And what they found is that the additional strength that came from adhesive cementation raised that 1 millimeter strength in resistance to actual failure to the same as the 1.5 that was cemented. So what does that mean? That means that adhesive cementation makes a huge difference in terms of the long-term sturdiness of these restorations. So dental alloys. There's really two ways that these can be classified. One is by nobility and one is by type. With nobility, it means something a little bit different, as you guys know, in dental than it does on the periodic table. It means that they're alloys that are called noble here do not corrode readily in the mouth. As you know, the high noble and noble alloys tend to be more expensive, and most laboratories sell them by weight. So it's hard to know exactly, either for you or for us in the laboratory, exactly how much a restoration is going to cost until we fabricate it, because we don't know how much. One other thing you can run into at times is with allergies. And in general, high noble alloys have less allergic reaction than base do. But there's a couple of variants on that. One is that it is possible to get nickel-free base metal alloys, which tends to help with patients who have been sensitized to nickel by jewelry. And on the other hand, sometimes high noble, especially high noble PFM alloys, have a lot of components in them, which could cause a potential allergic reaction. There are specific alloys that have been created that where the manufacturers try to limit the number of metals that have been alloyed to make it potentially less reactive. One of the things you can do if you want to do some testing is that you can maybe rent an ingot of the alloy from an uncast, in other words, ingot from your lab for skin testing if you need to. Well, nobility refers to composition, which of course affects the strength. Type pretty much refers to the physical properties. And it's interesting, we were just talking about zirconia, and look at this, a type 4 alloy, the strongest alloy we use in dental, is only showing 500 megapascals of strength. But what's different is, again, this is more ductile, so more tough, so it can absorb a certain amount of force through deflection before it fails. So, and we've used type 3 and type 4 in the mouth forever, so that kind of gives you an idea about what flexural strength, or in this case yield strength, we need. There are going to be some times where PFM might be the best restorative solution for your patient. You're like, what? 2026 and you're talking about PFMs? It's not just because I started out as the opaquer in a PFM lab in the 80s. It's because there are some times where you get a good result. If you have a really, really dark stump, we had a case one time we were working on where the prep looked like the same shade as a fir tree. I'm not kidding. I have no idea how it happened, and we needed a lot of blockout for that baby. So it turns out PFMs are 100% opacious. So they're kind of the nuclear option for dark substrates. Another thing to keep in mind is with your implant crowns, if you're doing a screw retain crown, most of the time your screw retain zirconias do have an abutment in them that could conceivably come uncemented, so to speak, or decemented, whatever you want to say. With PFMs and gold crowns, it's possible to cast them from a UCLA sleeve so they can't possibly delaminate. So that gives you another option. One other thing is that, I don't know if you guys have noticed this, but in some patients with a very strong bite, when you're doing, say, 18, 19, 20 with 19 as a ponic, sometimes you'll get breakage at the mesial of 19. No matter how thick you make your monolithic zirconia. Doesn't happen very often, but every once in a while. In those situations, I found that doing a non-precious PFM with big joints on the framework can, again, because of the ductility stand up in that situation where a monolithic didn't. Last but not least, if you do a PFM with a metal margin or a gold crown, as you know, because of that metal ductility, you can bring that to a fine point and get a very, very nice marginal adaptation. With gold, you can even use a little bit, use like a type 3 or type 2.5 and actually burnish that margin to get a really nice adaptation. Gold crowns. I had a friend, so this was back in the 90s. He still had a gold crown that his friend had done for him right after World War II, when it was his friend's crown that he did for boards back in those days. So like in 1946. So he literally had this crown for nearly 50 years with no problems, no caries. Obviously, he had good dental hygiene. So the main problem with gold crowns, if you think about it, is that they're ugly and they're expensive. But other than that, there's really nothing wrong with them. They're biocompatible. They're gentle on the opposing dentition. They're very difficult to break. So a lot of times, and they can be made pretty thin. So in areas where you really need strength and you don't need to be as concerned about cosmetics, these can be a great thing. And these are kind of the oldest crown. There's records that the ancient Egyptians were making gold crowns back in the day. So let's talk a little bit about prep design. This is kind of the ideal prep design for a layered restoration or a cemented lithium disilicate with a full cast or a monolithic zirconia. You could take these down to 0.8 of a millimeter. One of the things you want to watch out for with your preparations is that with any shaded ceramic, this area is very important. If the prep sticks out in this area, it's easy to get a headlight. So we want to avoid that. The other thing you'll notice about this is the rounded internal line angles. Whenever possible, this is ideal because if you think about it, the inside of the crown is going to be the negative of the preparation. So if you put a sharp corner on a preparation, then the inside of the crown, if it's well adapted, will have a sharp corner there too. And sharp corners are where stresses focus and can lead to fractures. So if you need to do sharp corners for retention where the ferrule's short or something, they're really best done with a metal restoration, because with a metal restoration, either a gold crown, it's ductile, so it's less likely to fracture. And with the PFM, we actually round the coping so the more brittle ceramic material doesn't have a sharp corner underneath it. Margin design, I guess we'll go from this way over. Shoulder bevels were designed for PFMs with metal margins or gold crowns. So if you're doing that kind of restoration, it's probably worth it. Otherwise, probably not worth the extra effort. A chamfer gets you a beautiful, a nice thick margin that's less prone to breakage and can also give a nicer shade transition. This is a nice default. With strong materials like monolithic zirconia, we can do a knife edge or a feather edge type margin. Keep in mind that most of the ceramic materials need a little bit of thickness. So if you need a really, really nice blend at this edge, you may need to thin it out a little bit after it's cemented. Here's some things we want to avoid. Exaggerated shoulders, especially exaggerated shoulders that have a little lip on them. It can be difficult to get really good adaptation on these. And we can tend right at the very edge of the margin, we can tend to have poor adaptation. So it's better to do like a millimeter is plenty on a chamfer. Undefined margins. It turns out if the margin isn't visible in the scan or the impression, it will not adapt accurately in the mouth. We talked about sharp corners, how we want to avoid that. And then we need to really watch out for draw. Of course, we want to avoid this because either we need to re-prep either you got to re-prep, take a new impression, or we re-prep it and send you a reduction coping, which you know is a little bit difficult. Or we're going to wind up with open margins because this has to draw. So this margin might wind up being open. So want to avoid that. Inadequate taper. So in other words, there's no undercut, but it's super duper parallel. If you want to do that, that's okay, especially with digital fabrication, we can make it work. But if it's got a feather edge or a knife edge margin, it can lead to opening here and there. Another thing to keep in mind is this going to be difficult to work on the laboratory, and it's going to be very difficult to seat in the mouth. So your best bet is to try to do get a total net taper on your preparation of 3 degrees per side, so a total of 6 degrees. That'll give you nice retention form and still make the case easy to deliver. Obviously, we need our bridges to draw, but I'm going to tell you one little trick I would recommend on this. If you cut a chamfer on a bridge, it gives your laboratory a little bit more flexibility. So if there is a slight undercut that you didn't see when you were preparing it, your laboratory can sometimes compensate for it by changing the path of insertion. So if you help yourself out with that, you'll get less calls about draw issues. Connector size, very important. This is the chart for what we'd want to use with high strength materials like zirconia, type 4 metal, that sort of thing. With lithium disilicate, we're going to need a little bit larger connectors. And you're like, why do I care about this? This is the laboratory's problem. Well, true. The one exception is if we have really limited restorative space. As you guys know, vertical height on a connector is much more important than horizontal width. So sometimes you may need to prep the margin a little bit deeper in the proximals, or maybe even remove a little bit of tissue to make sure that we have enough vertical height to get a nice, strong connector. What do we mean by a strong connector? Well, two things. If we increase the inciso-gingival height of a contour, of a connector, the strength increases by the cube of the change multiple. You're like, what does that mean? So this means that if we take a connector and it was only 1.5 millimeters tall, we make it 3 millimeters tall, that joint is 8 times as strong. On the other hand, if we take it from 1.5 millimeters width to 3 millimeters of width, we doubled it, but it only makes it double as strong. So getting more vertical height on our connectors is really important. We also want to think about how the number of ponics increases the load on the connectors. So if we say that whatever this load amount is X, when we put one more ponic in, now we're up to 8X load on these joints. So you can see these joints are going to need to be bigger and especially taller than these. So we need to think through all this kind of stuff. Once we get much beyond three ponics, there really isn't a material that exists that we can make strong enough to resist the kind of forces it's going to see. Man. There's a fear, I think, sometimes that hard materials like zirconia lead to excessive wear. But what this study shows and what's been found is that it doesn't have so much to do with how hard the material is. It has to do with how smooth it is. So if you need to make adjustments, you can see that the wear of a highly polished zirconia here is actually less than ceramic or glazed zirconia. The polished zirconia is best. So how does this affect you? A, us laboratories need to polish it well. B, if you make adjustments, make sure you have an appropriate polishing kit for the materials you're using. Couple other little tricks. If you have to cut off a zirconia or a crown, you're going to want to use a new fine diamond, lots of irrigation, and let the burr do the work. Don't push too hard because, I mean, if you're cutting off the crown, I guess it doesn't matter if it fractures, but otherwise, localized overheating can lead to fracturing. And the other thing is, you probably noticed this, your diamond gets too hot, the adhesive that holds the diamonds onto the metal burr melts, and then all your diamonds go away, which is frustrating. So cementation, all the articles I've seen says that when you're luting, if you use a resin modified glass ionomer, you'll get generally a better result because they do have nice adhesion, but they also have that fluoride release. We want to use adhesive cementation whenever possible for lithium silicate or disilicate. When we're bonding zirconia, so either let's say you have a really short prep or some other contraindication, you'll want to make sure that you use an MDP primer. The other thing I would say is that zirconia loves phosphates. So the phosphate in saliva and different things like that can tend to bond and kind of chemically plug it up. So if you use a one of the generally like Ivoclean or something like that, a generally available cleaning material before you cement it, you'll get better results because then the phosphate groups are open and ready to receive that MDP primer. The P is for phosphate. And then when you're using opaque materials and bonding, it's probably better to use a dual cure. I know there's sometimes concern about shade shift. I'd always recommend using a clear material anyhow, because cement's effect on shade is unpredictable. So we need to control the shade in the laboratory, as opposed to meaning that you have to do it with the cement. So, but with a more opacious material, there's always a concern, especially in thicker areas, that the light won't penetrate for a pure light cure material. Whereas if you use a dual cure, you can be assured that you'll get that full cure that you need. So we're going to go through digital workflow really quick, just in case you guys have never seen this before. So in our laboratories, any monolithics that we're doing, in most labs, almost any fixed restorations we're doing these days, we want to do a digital workflow. So we got to figure out some way to digitize it. So the best way is you scan it with an intraoral scanner, and then it starts out digital. But if you provide us with a physical impression, that's okay. We can either scan the impression or pour a model and scan that and get the case into digital space. So then our first step is going to be, once we've got it scanned, is to do a design. Most laboratories use 3Shape or exocad. This is what 3Shape looks like. And your laboratory usually gets a initial proposal from the software, and then that proposal needs to be tweaked for proper form and function. One of the things that you can work with your laboratory on is that, you know how in the old days with analog, there were different, like I want one strip of mylar to pull through and different things like that. Well, we can set the contact and occlusion offset and the fit as we can control that in hundreds of a millimeter. So you can work with your laboratory to, just like you had preferences in the analog world, you can have digital preferences to get more predictable results. Once a design is done, we'll do a process called nesting, where the design is loaded in the software that controls either the CNC mill in this case or the printer. One of the interesting things that I didn't know when I first got going is that we talked about that zirconia pre-centered, it shrinks during the centering process. So it needs to be expanded. Interestingly, it's not designed expanded. It's designed to the size that you want. And the actual nesting software is what expands it. So we key in the expansion factor on the side of the disk, and then the nesting software enlarges it. It's always interesting when you're cutting milled units out of the zirconia puck. You look at them, especially molars, you're like, man, this thing looks gigantic, because that 17% is a lot visually, at least when you're used to things being a given way. So anyhow, once it's milled, we'll clean it very carefully, remove any milling debris, dry it if it was wet milled, and then center it. The centering process is extremely important. This is important for fit and contour. This is important for physical properties. The physical properties of your zirconia crown are determined by the reliability of the centering. It's helpful if we center it properly. So lithium disilicate, there's basically, I mean, you guys know, and there you can hand wax it, invest it, and press it. But these days in the digital world, there's a kind of a hybrid analog workflow and a fully digital workflow. So with the hybrid workflow, you design the case, mill the wax, invest it, and press it. And then in the fully digital process, you can see the blue blocks here. These are semi-centered lithium disilicate. So it's milled and then it's centered in the in the porcelain furnace. I think that this process is still a little bit more common in laboratories because these beat up the spindle. The spindles are probably the most expensive part of the milling machine that can wear out. And then they're kind of a pain to replace and then get the accuracy back where you need it. So a lot of times in laboratories, we try to avoid, interestingly, zirconia is kind of the kindest. PMMA is fairly hard on the spindles, and any grinding process is extremely hard on the spindles. So, but of course, you can achieve a very good result with both. This one, you got to control the investment expansion and then subsequent contraction once everything's centered.